The data gathered by GPM and its international constellation of satellites has generated an unprecedented global view of rain and snow. We can see daily patterns, seasonal movements, the rain in our own backyard, and weather sweeping the continent. We can analyze regional hazards and precipitation that connects the globe. We can build up months of data to years and decades to look at how precipitation will change in a changing climate. And we can explore precipitation from pole to pole in a snapshot of a single week. Daily rainstorms are a constant near the equator.
The interesting things you see when you look at this is the daily pulse in convection, what you might call the popcorn. So for example, over Africa, you see this regular pulsation of convection, and then there are the longer-lived events, which are squall lines. Because this happens to be during August, what we can see is the squall lines which move across the continent, starting in Ethiopia, and when they come off the coast, they're known as easterly waves. These are the precursors for some of the hurricanes that we see in the United States. As you follow them across, the same kind of popcorn is taking place in South America. And if you watch carefully, you can see that line of convection starts along the coast in the afternoon and starts propagating in. And if you watch the pulsing, what you see is it takes about 2 days for those squall lines in South America over the Amazon to reach the Andes Mountains, at which point they sort of die out because they interact with this very steep topography.
The Atlantic hurricane season was relatively quiet in 2014, but GPM was able to track storms into higher latitudes that nevertheless had unexpected impacts.
One of the things we can observe with the 2014 hurricane season is actually Hurricane Bertha, which you see here. Now, it was kind of an unimpressive storm, but as you track it across the Atlantic, what you can see is that it caused massive flooding and wind damage in the UK. And so by being able to observe tropical cyclones in their infancy in the tropics and see how they move all the way to the high latitudes, it gives us really important clues into how storms develop and intensify all the way into the higher latitudes and as extratropical systems.
And it's really important to know what is happening in those high latitudes because that's where the majority of people live. It's where the populations are. And so being able to measure everything from the very light rain, which tends to occur at these high latitudes, and the falling snow, as well as the very heavy precipitation that occurs throughout the world. We have this data from the Global Precipitation Measurement Mission.
Meanwhile, the Pacific Ocean saw a steady barrage of tropical cyclones slamming into Hawaii, the Philippines, and Japan.
Here you can see the different cyclones and typhoons as they move in the Pacific Ocean, one after another. What's also important about these is knowing where they are over the vast ocean so that once they get closer to land, operational users can make decisions about whether to evacuate people or not.
For example, here we see Super Typhoon Halong, which recurved and then crossed Japan and started to interact with the mid-latitude cold front. Once it did that, it went, as we say, extratropical, and we can trace it all the way up into the northern Pacific Ocean.
As we head south through Asia, seasonal rains drench India and its surrounding areas.
One of the things that we can observe about this data set is where and when rain is happening. And by being able to see, for example, this huge cluster of storms from the monsoons, we can understand where we might get heavy rainfall that leads to landslides and flooding. In fact, what we observed during this time is actually a landslide that caused 150 fatalities. You can actually see what's happening just 4 hours after it occurred. And that near real-time capability is critical for different disaster managers, understanding where we're getting flooding and landslides around the world. And when we look at the longer term, where we're getting the absence of rain, where we have droughts, and understanding how those drought conditions are continuing or may be improved because of rainfall that's coming.
With GPM, we can look at how precipitation impacts very large populations and shed new light on the area where almost no one lives.
From South America, if we look to the south, you see the ocean that runs nearly around the entire globe, which we call the Southern Ocean. This is really sort of the terra incognita of precipitation as far as I'm concerned. The Southern Ocean has almost no land and very few ships. It's a really challenging place. You don't go there unless you have to. As a result, we know very little about the meteorology and the precipitation. When you look at that zone, what you see is the blue and darker purpley colors, which represent snow. Because this is a southern hemisphere winter, there's some snow that we see. We've known about these storms for a long time in terms of the cloud patterns, but this is the first time we have a really great visualization of the rain, which is underneath. This is one of the features of these data sets, is it's like an X-ray that looks through the clouds and actually sees the rain.
When you take a step back and look at this data set from a global perspective, you can see the precipitation at the tropics that looks like these popcorn convective events, as well as these long-lasting frontal systems in the high latitudes. And it's with this data that we can start to understand precipitation globally and see how it interacts with humans and with the science and understanding it better.